Hello and welcome. This is another video in this series on basic topics geared for my ITS2300 Data Networking class. In this particular video, we talk about network address translation. And so let's jump into, actually first, we're going to jump into the table of contents for our TCP/IP Illustrated book. And in this case, network address translation in this book is grouped together with firewalls in Chapter 7. For this particular this particular overview, the only thing you really need is the introduction, 7.3, section 7.3 introduction, and the actual 7.3.1 traditional NAT, basic NAT and NAPT. There are a number of subsections underneath that, like 7.3.1.1, 7.3.1.2, and so on, that talk about NAT interaction with protocols we haven't discussed yet. So we're not. That's not a level of detail we're going to go into. So what you want to do is focus on the introduction of network address translation, and then just the introduction to the first section, 7.3.1. That'll give you the information you need. So let's look at an example here, and I'm going to see if this works. Yep, I'll try to keep myself out of the way a little bit here. So what I've done here, I think I zoom it in one. Whoops, zoom it in one more. So what I've done here is I've created a network where I've got a couple of computers on private addresses. They're behind a network address translator / router. The router has an external address on its internet connection, and then there's a server out here that we're going to access, a web server out here that we're going to access from our PCs behind the network address translator. So what I'm going to do here is sort of try to reproduce some of the packets that we would see, and this is something we will do in the ITS2300 lab, is to look at what these packets actually contain. So let's say our first PC here is going to access that web server. So it's going to create a packet with its address as the source, 192.168.1.1. And I'm going to put the port number behind here. So let's say this is 41,000. So remember that at the transport layer where we're doing this, and this would be TCP packets. In addition to the IP address, I have to add a port number. So in this case, this is the port number that the browser got from the operating system randomly, that identifies that particular browser tab or window. Is the one that initiated this connection to the web server over on that side over here, So for the source, that's usually a randomly assigned port. The destination of this packet, of course, will be 132.235.1.1, and port 443, which is the secure HTTPS secure web protocol port. So some ports, especially the low numbered ones, by standards are assigned to particular protocols. You don't have to set your servers up that way, but that's how browsers sort of default. That's why, as a user, you never have to type in 443 as the port number into the browser, because it assumes that if you type HTTPS. All right, so here's our packet. I'm going to put an arrow here. So this is the packet that's being sent out towards the server. And this packet is going to have to be translated by the network address translator. So we're going to grab all of this and take a look and see what happens over here. So this packet travels through the network address translator. If this source address went out into the internet, it would become useless because there's no route that would tell me where to go to find this computer, because these are private addresses. They're not in the routing tables. They're used in many, many different places, so there's no way to find this. So the network address translator needs to do a couple of things. The first thing it's going to do is it's going to translate the source address to its external address, the one that is reachable, 132.235.67.19. So when this arrives at the web server, it will appear to have come from the NAT. That's how the reply can get back. Of course, the network address translator is not going to do anything with the destination. That wouldn't make any sense, because that's the machine I'm trying to reach. Now, will the address translator also change the port number? Most NAT devices today are able to do that, and I'll show you the reason for that in just a second. Many of them will only change the port number if they have to, if there's a conflict that would otherwise make it impossible to figure out the inbound packets properly. The NAT device will then also record that it translated 192.168.1.1 port 41,000, I keep doing this, to 132.235.67.19, and let's assume it didn't change the port, so it'll still be 41,000. Right? That entry will become important just a minute when packets arrive at the network address translator. This is the minimum information needed to make sure that we figure this, that we that returning packets can be correctly routed to the correct IP address and port. Because network address translators also provide, in effect, a security packet filtering function, you can expand that, right? So you could, and some network address translators will do this, you could add the destination address and possibly port number to this translation table and say, I'm only going to recognize packets coming in if they're actually coming from the same computer that we were contacting from the inside of the. That isn't necessary for the operation as a network address translator, but it would improve the security properties of the network address translator. All right, so let's grab this packet and duplicate it real quick, and to see what happens. Where did I put this? Let's grab you, move you out of the way a little bit, and grab you. So let's see what happens if, by some weird coincidence, our other PC decides to use the same port number and access the same web server. And in this case, all it has to do is use the same port number, which there are like 60,000 of them, so it's not likely, but it will happen from time to time, right? And so when this packet gets translated, I'm going to move the translation table out of the way a little bit here. So when this packet gets translated, again, I need to change the source IP address to the IP address of our NAT device. And at this point, the network address translator would realize that it has a problem, that it already has a translation of that type. It already has an entry 132.235 to 67.19 port 41,000. It can't assign and it can't use that one again. So in this case, it would change this to a totally different number. Let's say 20,000. And it would then make an entry here that says 192.168.1.1 used port 41,000 for an outbound connection, and I've translated to 132.235.67.19, and I've changed the port to 20,000. Cool. Right. And again, it could record more information if it wanted to be more specific, and therefore provide an extra layer of security where only a direct response to the packet that was being sent out is actually allowed back in, as opposed to anything that's trying to go to that same port and IP address. So let's take a look and see how this works. I should say too, you might wonder why would I record the IP address, because there's only one IP address assigned to the network address translator. That's the way I have this drawn up. Larger network address translators, like the ones that Ohio University runs for its wireless network and so on, actually have a pool of addresses, of public addresses they translate to. So you would, it is very easy and for larger NATs, very appropriate for them to have multiple external addresses. So these translation tables also always specify what the address is. Right. So let's pick this. For sake of argument, let's grab the second packet here. I'm going to just grab this and duplicate it. And so how does this packet get back? What happens when this packet tries to return? Let's see if I can do this easily. Oh, I could have flipped it, couldn't I? Yeah, there you go. So what does this packet look like when the server replies, right? It's going to have to take the source, and it's going to have to send the traffic back to where it came from. So it is going to send traffic to 132.235.67.19 port 20,000. And it's going to, of course, put its own address in here as 132.235.1.1 port 443. Right, so this packet is now traveling back from the server, from this guy here, back to. It is supposed to get to our second PC down here. So this packet now arrives at the network address translator. The network address translator will look at the destination entry and try to match it to something in its translation table. So this is where the security aspect of the network address translator comes in, right? An inbound packet has to match all the information the network address translator recorded. So at a minimum, it would be the address and port number, that the outbound packet used. If I wanted to make it more secure, I could add columns to this translation table and also record where the packet was going, and allow this translation backwards to happen only if packets come in from the same place that they went to. So they're different. There's no standards about this. Every manufacturer can program their network address translation device differently. And obviously, if a packet were to come in that doesn't match any of these entries, the network address translator knows it's not a reply to something that one of the local PCs did, so it's going to discard the packet. It might send an error message depending on how it's configured. In most cases, it won't. But the standards have a mechanism through the ICMP protocol we're going to get to at some later point to basically send out an error message saying you can't do that. Right. So again, this translation exists or has to be performed because these public addresses in IPv4 are in terribly short supply, and so the only way to serve all the computers and handheld devices and Internet of Things devices, security cameras, sensors, and so on, to serve all of those devices, we have to do this because we don't have enough IPv4 addresses. In IPv6, this type of translation is unnecessary. You still want to do the filtering, but you don't have to do address translation, which generates some odd problems for some types of protocols that rely in some way on the port number, in particular, of the connection to not be modified, and because the network address translator to function properly is randomly going to, if there's a conflict in the translation table, the network's address translator will somewhat randomly modify the port number. If a protocol does not expect that to happen, then we run into a situation where that protocol stops working sort of randomly, which is bad. So for IPv6, we don't have to do address translation. There's really no reason to do that. There's some corner cases where that might be useful, but there are very few of those. But you still want to do packet filtering, very similar to what we're doing here. We basically keep track of what packets went out, and you allow packets back in only if they're replying in some predictable way to the traffic that went out. So those are kind of the two aspects to keep in mind for network address translation. As always, there are examples in the section in the book, and you want to study those. Probably, again, this is one of those videos that you probably want to go back and just pause and make sure that each of the things that are sort of typed in as I went actually makes sense to you, and that you sort of have a sense of what happens and complete this path backwards, going, how does that work? How does everything end up back here at this PC? Well, I hope this video was useful for you, and I will see you in the next one.